Now, as a second topic, let's solve some example problems, including point moment, hinge, and point force. So let's first consider point moment problem. So in this point moment problem, we have a beam which has simply supported at both ends, and there is one point moment at distance a from the left end. And at a first glance it looks a little bit confusing, but because like until now you've mostly seen the force problems, right? Distributed loading or point force, but here, yeah, somehow you have a point moment. But like, even though we can like imagine point moment problem, can we realize this in real life? And I think yes. When you have this beam, and if you have a cross shaped driver, and if you plug in your driver and try to rotate this, yeah, it can be equivalent to point moment problem, right? And you have, yeah, this support so that you cannot move this y direction. And I think after applying this kind of torque, yeah, it'll, yeah, bend something like this. Okay, so yeah, regarding how the beam bends, yeah, we're gonna discuss about this in next chapter. But today, what we're gonna do is we'll simply obtain force diagram and moment diagram. So as I told you, we have to use the rules 1, 2, 3. But before using rule 1, 2, 3, we have to get reactions and moment from statics, and determine the reaction forces at both ends. And because this is simply supported beam, you can immediately see that m must be 0 at left hand and right hand. And if you draw free body diagram except the support, yeah, you're gonna have ay and cy unknown force, and you have external loading me. Now to obtain cy and ay, yeah, because there is no external force, we have to rely on the moment equilibrium first. So regarding the moment equilibrium, let's take a point as a reference and try to consider m summation at a, and we're gonna take as we have done until now, we're gonna take counterclockwise direction moment as positive sign. So for that, we have L multiplied by Cy as a counterclockwise torque. We have ME external moment as a counterclockwise moment, and if you sum these two up, it must be 0. Then from here we obtain Cy must be minus ME over L. Now we have same thing for AY. So let's take C point as a reference and try to get moment summation. And with respect to C point, we have clockwise torque from AY, and you multiply AY to the length L from the point C. Then you have a minus LAY from the AY force, and you have counterclockwise ME, and they have to summed up to be 0, and AY is ME divided by L. And it's also consistent with force equilibrium. AY CY must be 0, so you have to have negative opposite sign and same magnitude for AY and CY, and this is our answer. After defining our AY and CY reactions, then you have to use rule 1, 2, 3 to obtain V and M diagram. So from left we have upward force ME over L, yeah, this is A. And for the C point, even though we take upward as our unknown direction, we obtained negative force, so that you can realize that the force is downward. Now if you recall the sign convention for V, you can see that both A and C have positive V. Okay, yeah, because it's downward on right facing surface, it's upward in left facing surface. So both A and C have the same V, and moment are 0, as I told you. So at x equal A, when you have point moment, the discontinuity in force must be 0, discontinuity in moment must be minus ME. So regarding Bx, yeah, we have left hand and right hand, and we don't have any distributed loading for this problem. So you have zero slope. So this is the answer. Very simple. Regarding m as a function of x, yeah, what you expect is, yeah, we have same slope. So you're gonna have a slope, that corresponds to the magnitude of v, and there is a jump, and this jump should be correspond to negative me. So this will be our force and moment diagram. Of course, depending on a, the maximum and the maximum and minimum of this m diagram can be different, but graphically this is what you can expect out of point moment problem with simply support at both left hand, right hand. Now let's move on to and solve a hinge problem. Okay, so when you first encounter hinge problem, it looks a little bit confusing, but if you stick to the basic principle, yeah, you can solve this problem without difficulty. So for this problem, you have rigid wall cantilevered support at A, you have a simple support at C, you have a hinge at B point, and dimension is given as L and A and L minus A. Yeah, distance from AB, distance for BC, and you have uniform distributed loading Qx, and this magnitude is W0. So to solve this problem, you have to, of course, get the reaction force and moment first from simple statics. So what we're gonna do is we're gonna split the problem into two parts. So we're gonna take AB part and BC part separately. For AB part, because we have rigid wall, so we have to consider MA and AY from the wall A, and from the hinge, the boundary condition for hinge is m equals 0. We can only have shear force By, and this is the free body diagram for the left part. For the right part, yeah, this By and this Vi is action reaction principle, so they have like a same magnitude but opposite direction. And we have support from C, so let's call this as a Cy, upward force, and we have W0 from the top. Okay, so regarding the left body, what you can see is if you sum up force in y direction, force sum should be 0, and 0, and if you consider summation of the y direction force, you have to consider AY. You have to consider force from top. So the force from top is W0 multiplied by A, W0 multiplied by length A. And what are the other force? I think I'm doing the lecture note in opposite way. Let's consider the the right side object first, because it has a simpler free body diagram. For this one, we don't have a moment because there is no moment in the right hand side. So regarding this right hand side object, what you can see here is this is completely symmetric problem. You have a By and Cy, and loading is uniformly distributed. Okay, and By Cy must be half of the force from the top, and half of the force from the top is half multiplied by W0 multiplied by length L minus A. So we can obtain this very easily from statics. Then what you can see is By is same as half W0 L minus A. So when you obtain the summation of force for the left hand side body, you have AY upward, you have negative By, and the magnitude of By is half W0 L minus A, and you also have the force from the top, W0 multiplied by A. So if you massage this equation, what you're gonna get is AY will be half W0 L plus A after doing this calculation. Now after figuring out AY, it's time to figure out MA. So what you're gonna do is we're gonna take some reference point at A, and we're gonna do summation of the moment, and the moment summation with respect to A point must be 0. So with respect to A, we have moment MA, which is clockwise, so we put minus MA, and we have By multiplied by length A. So we have minus BYA because this is clockwise torque with respect to A point. And we have W0 multiplied by A over 2. Yeah, for this simple uniformly distributed loading, yeah, we can take this as W0 A point force to make statically equivalent problem. Then what you can realize is with respect to A point, yeah, it's A over 2 multiplied by force, and the sign must be minus because it's clockwise torque again. So after massaging this equation, I have to plug in the value for By and rearrange the equation for MA. After rearrangement, you obtain MA equals to be negative half W0 LA. So this is how we obtain unknown reactions By, Ay, or Ma. Okay, so this is how we solve the problem using like divide and conquer strategy. Instead of that, what you can do is following. So you can take the entire body and take this as a our system of interest, and you can do moment summation with respect to A point. Then you have clockwise MA, you have the entire force W0L multiplied by L over 2, yeah, and you which is clockwise, and you have Cy multiplied by L, which is counterclockwise torque with respect to A, and they summed up to be 0, and you can obtain MA from this free body diagram, and answer must be same. So depending on your convenience, you can choose either consider the entire body or consider the like a small piece out of the entire body. It's your choice, but your answer must be same whatever free body diagram and whatever sub-volume you are taking. So after obtaining AY, BY, CY, and MA, this is your final free body diagram. Okay. So and after looking at this free body diagram, you have to check and always recall the sign convention for V and sign convention for M. So what you can see here is A point and B point. You have positive V because it's upward at left-hand face, and you have positive V at B point because you have downward force at right facing surface. And you can see that these action and reaction pair, downward and upward force, according to our sign convention, they have same sign Bx at B point. And regarding the C, it's upward at right facing surface, so that you can see that Bx must be negative at C point. Yeah, so this is the sign for Bx. And regarding the M, you have 0M here, and you have to have negative minus half W0LA for A point. So yeah, this is A and B and C point value for B and M. So after recognizing these three values, yeah, so for A point you have half W0L plus A, for B point you have half W0L minus A, and for C point you have you take this number minus half W0L minus A. So you take 3 point, and what you're gonna do is you can connect all these dots. These are points where the value for V exactly, and how you connect. You have to connect using the rule between distributed loading and the slope of the V. And what you can see here is we have constant and uniform distributed loading. The slope must be uniform for entire beam. So yeah, this is gonna be your answer. Yeah, this is what you're gonna get in the full range of the beam. And from this V value, and you have this relationship M prime must be V, so you can figure out many things. And what you can see from here is you have MA equals to be negative some number. You plug in that number here, and MB must be 0. This is the point where you have the hinge, and you have MC at 0. This is the point where you have the simply supported boundary. So from A to B, you have positive V, but the magnitude of positive V is decreasing, so you can expect that slope is decreasing. From B to C, yeah, you have positive slope, positive V first, and it becomes 0, and it becomes negative. So when V reaches 0, the slope for M must reaches to be 0. This is V equals 0 point, and the slope is 0 for dm dx, and you have this smooth connection of M. The slope changes from quite large positive number to 0 and quite large negative number. So this is how you draw moment diagram as a function of position x. Okay, so with this, yeah, we discussed about a hinge problem. As a last example, let's consider point force problem, and it's quite I would say simple compared to previous problem. So so for this point force problem, you have external force P upward at B point, and we have point moment P E times L at the C point, and we have rigid wall at the A point and cantilevered support at A point. So to solve this problem, yeah, we have to solve the reaction force and moment first. So we have reaction force unknown, reaction force AY, unknown reaction moment MA at the left hand side, and we have two external loading. So from the force balance in Y direction, yeah, we can very easily obtain that AY must be minus PE to make a balance between external force and the reaction along the Y direction. And if you consider moment equilibria with respect to A point, then you have to sum up all the moment. So AY does not exert any torque at A point. MY exert minus MA because it's clockwise rotation. Clockwise torque, you have P dot A, P multiplied by length A, which is counterclockwise torque with respect to A. You have PL, this is the moment applied at C point. Please do not confuse. This is the force multiplied by length L has the unit of moment. It's basically the magnitude of point moment applied at C point. Okay, so this is counterclockwise. You have negative sign here, and they must be summed up to be 0, so that your MA turns out to be minus PE multiplied by L minus A. Of course, when we make this problem instead of PL, you can simply plug in like some number M0, but instead of putting M0, if somebody put P multiplied by L as the magnitude of the point moment at C, you can obtain the answer for MA much easier, and your final answer will be easier. That's why the designer of this problem set the magnitude of point moment at C as PL. Anyway, after obtaining the moment at A point, so you obtain minus PL minus A. Originally set this as the direction of MA. So finally, this is the moment you obtained after solving the mechanical equilibrium. About AY, you set upward direction as unknown direction, but you obtained minus P. So finally you have force pointing downward at A point. Okay, now after recognizing all reaction forces and moment, and after also recall the sign convention for V and M, what you have to do is you have to set the values at A and C and B point. So A point moment should be negative this number, because this is smiley facing moment is the positive sign, so it has negative sign. Regarding VA, for left facing surface, upward is the positive, so you have negative P as a V at point C. Regarding point C, we have 0 shear force V, and we have moment which is minus PL, because this is the the opposite sign of the positive sign convention, and at B point we expect delta B of PE, because P is upward force. For downward force is this. For upward force, you have to have PE. So this is what you're gonna get. And regarding Q is exactly 0 for entire range. Okay, so what you can expect is, after recognizing minus PE, after recognizing V is 0 at C point, at A point, you should have constant V at AB region and BC region, because QX equals to V0. And how you can solve this problem? You have this one more condition, like delta V, discontinuity in V must be PE. So V must be jumped by PE, and this is consistent with the value at A and C and B. Okay, so that's the first diagram we wanted for. After obtaining the first diagram, it's quite simple to obtain moment diagram. So moment at C is minus PE multiplied by L, quite significant negative number. And regarding the MA, we have P multiplied by L minus A, and L minus A is smaller than L, so you can expect that similar magnitude negative number for M. And from the moment diagram, what you can expect is, because V is 0 from A to L, the slope must be 0 for M, and from from 0 to A point, you expect dm dx equals to V, or it should be straight line. Okay, and the slope is the same as minus PE. So this is what you can expect out of this point force problem. Okay, so in the second video, I discussed about point moment problem and point hinge problem. No, it's not point hinge, just a hinge problem, and point force problem, which at a first glance looks a little bit confusing, but after figuring out the free body diagram and apply the rule carefully, we just learned that we can obtain the shear force and moment diagram relatively easily. Okay, so with that, let me finish my second video for today's content.